Okay, welcome back, everyone. Before we start today, does anybody have any questions for me? How's it going with the assignment? Going? Good. So hopefully most of you have at least started it, if not finished it yet. The plan is to have assignment 2 available for you at the beginning of next week. So in case you're stuck with nothing to do after submitting assignment 1, you can immediately start on assignment 2. So today we're going to have a slower class. We'll slow things down a little bit. Look at a couple of things that we've done before in a slightly different way. And then basically just go through a few examples of using some of the techniques that we've learned. So first thing I would like to look at before continuing is this famous thing that's called Pascal's triangle. And I've hinted at it and drawn pictures of it, some parts of it. But Pascal's triangle is this sort of triangle of numbers that come in rows. The first row has 1, the second row has 2, the third row has 3, and so on. But it's probably better to label them the 0th row, the 1st row, the 2nd row, the 3rd row, and so on. And what are these numbers that are here? Well, up in the 0th row, the number that you have is just 0, choose 0. So how many subsets of size 0 are there of a set of size 0? Well, there's 1 of them. And then the second row is 1, choose 0, and 1, choose 1. How many subsets of size 0 of a set of size 1? There's 1 of those. It's only the empty set. And how many subsets of size 1? Well, it's the set itself. So those two numbers are 1 and 1. And so on and so forth. So the second row is 2, choose 0. The row with index 2 is 2, choose 0, 2, choose 1, 2, choose 2. And then the next row is 3, choose 0, 3, choose 1, 3, choose 2, 3, choose 3, and so on. And usually you actually write the numbers down like this. And it's really easy to do this for a few reasons. But the main one is a theorem that we saw, which was Pascal's identity. Pascal's identity told us that n plus 1 choose k is equal to n choose k plus n choose k minus 1. Okay? And that was because if you have a set of n plus 1 people, you call one of them special, and you look at all of the ways you can choose k people where none of them is special, and all of the ways where you can choose k people where you include the special one in your choice. Okay? What does that have to do with this triangle? Well, it gives us an easy way to compute the next row of this triangle, because it tells us that if I want to know one of the entries in row n plus 1, I can get that from 2 of the entries in row n. So for example, here's this entry 10 in row 0, 1, 2, 3, 4, 5. And where did that come from? Well, it is, so this is 5 is n plus 1, and here is, so this is supposed to be 0, 1, 2. This is 5 choose 2 here, and what's 5 choose 2? Well, it's 4 choose 2 plus 4 choose 1. Okay. So it always looks like that. Okay, so that's the relationship between Pascal's identity and Pascal's triangle. And it's a little bit surprising in some sense that these weird binomial coefficients that if you write down an explicit formula for them, there's these factorials in there, so there's multiplication involved. But if you want to get them all and list them all, you just do additions, which is a little bit surprising. Okay. So let's look at Newton's binomial theorem and say, what did that say? So Newton's binomial theorem, that was about x plus y to the n, and that says that that's equal to the sum k equals 0 to n of n choose k, x to the n minus k, y to the k. Over here, what does that mean in Pascal's triangle? Well, that says that if I have one of these binomial things, in order to read off the coefficients, I just read off one row of this triangle. Okay. So for example, here we are at 6. So x plus y to the 6 is equal to x to the 6 plus 6x to the 5, y to the 1 plus 15x to the 4, y to the 2 plus 20, y to the 3, x to the 3, y to the 3 plus 15, x to the 2, y to the 4 plus 6, x, y to the 5 plus y to the 6. Okay. So that's the interpretation of Newton's binomial theorem. If you want to expand this thing, you can just read off a row of this triangle. You get the coefficients that way. Okay. So this just basically says binomial coefficients of x plus y to the n are listed in a very specific order in row n. We saw another theorem that said, we proved it actually two different ways. The sum k equals 0 to n of n choose k. So if I count all the subsets of size 0 and all the subsets of size 1 and all the subsets of size 2, size 3, and so on, what do I get? Yep. It's 2 to the n. Because at the end of this process, I've counted every possible subset of an n-element set, and those we kind of saw, well, those are 2 to the n. You can prove it using Newton's binomial theorem, or this sort of bijection between those and, I mean, just directly using the product rule, I guess, where you just look at the elements one at a time and decide whether or not they're going to take part in the subset. You have n choices to make. For each choice, you have 2 options, so you get 2 to the n possible subsets this way. Okay. All right. So what does this say? This just says the sum of all values in row n is 2 to the n. That's in the Pascal version of this. And again, it's a really strange thing that you wouldn't expect by looking at it, because I don't see nice even numbers here or powers of 2 or anything, but you add up a row and you get a power of 2. We also saw sort of a baby result that n choose k is equal to n choose n minus k. What does that mean in terms of this triangle here? Yep. You have symmetry down the middle, or if you want to focus on the particular row that we're talking about, the nth row, it means that if I read it from right to left, it's the same as if I read it from left to right, the same as if I read it from right to left. Yeah, or it's a palindrome if you like that language. Okay. And here's one that we saw, which was if I take the sum k equals 0, so this is a special application of Vandermon's identity of n choose k squared, then I get 2n choose n. Okay. So over here on the left, I'm summing up the squares of the value in a row, and that number shows up somewhere else. It shows up right in the middle of the row 2n. Okay. So for example, so what do we got? 0, 1, 2, 3. If I sum up 1 plus 9 plus 9 plus 1 is 20. That's kind of a surprising thing about this. Okay. And really, when I say the middle of the row, it really is the unique number in the middle of the row. Why is it unique? Well, because 2n is an even number, and the 2nth row has 2n plus 1 entries, so an odd number of entries, so there really is one squarely in the middle when you apply this thing. Okay, and as a thought exercise to do on your own, try and interpret Vandermon's identity in terms of this thing. See if it has a reasonable interpretation. All right. Any questions so far? No? All right, good. So now let's look at a couple of basically counting problems where we can apply some of these techniques. So how many orderings, and I should say sort of distinct orderings of the word success are there? So success has 1, 2, 3, 4, 5, 6, 7 letters in it. So how many different ways are there to order those letters? And more specifically, how many ways can you do it, or how many distinct sort of words can you get from this? So is there an obvious answer or an obviously incorrect answer? Yeah. Yeah. So 7 factorial seems like what we want, right? I mean, it's really these orderings seem to mean permutations, and there's 7 letters, so there's 7 factorial possible permutations of them. So for example, one of the permutations could be 1, 2, 3, 4, 5, 6, 7, which gives us the word success. And another permutation could be 7, 2, 3, 4, 5, 1, 6, which gives us the word, well, at position 7 is an S, 2 is a U, C, C, E at position 1 is an S, and at position 6 is an S. Gives us the same word. So if I just count the number of permutations of seven distinct things, then I will see, for example, this permutation, the standard one, the identity permutation, where everything stays where it started, and then I'll see this one. But if I apply this permutation to this word success, I get the same word back. And if I apply this permutation to the word success, I get the same one back. So if I'm counting just the number of permutations, then I've counted this word at least twice, and I shouldn't have done that. Okay. So permutations work great when you have a sequence of distinct elements and you want to know how many different ways can you order them. But when the elements are not distinct, you have some more work to do. Okay. So any suggestions on how to proceed? Yep. No, why 3 factorial? Because S occurs 3 times? No, that's too simple. There are 4 unique letters, yes, but it's not 4 factorial because if I just write down the unique letters, S, U, C, E, then there's different ways to put in the extras that give you different things. So it's more than 4 factorial, it's less than 7 factorial. Yeah. Divide by 3 factorial and 2 factorial, maybe. Yeah.
Would it be 7 factorial minus 723?
It's hardly ever minus like that, because usually the minus doesn't do it. So there's a good answer here. So one way to do it is to try and eliminate symmetries, which is you say, okay, I'll look at all the 7 factorial permutations of this thing, and maybe I'll be able to show that actually every word here is generated exactly the same number of times by these permutations, and then you'll get an answer like 7 factorial divided by the number of times each word appears. So that's one way to do it. It can be tricky to make sure you're doing that right. So let's just go with basically the first thing we learned, first technique, the one you've been using on your assignment if you've been doing it. Product rule. Let's just figure out how to write down these things. So I want to write down one of these words here that I can generate from these letters. So I've got 3 S's, I've got 2 C's, I've got an E, and I've got a U. So in the end, I know that this word is, the word that I get is going to be 7 characters long. So you can think of, there's places to put the letters. And so the first thing I'll do is place the S's. Okay. So step 1, choose the locations of the 3 S's. So for example, I could put an S here, and an S there. So how many ways are there to do step 1? 7, choose 3. Okay. Step 2. Choose the locations of the 2 C's. So I've already placed the 3 S's. Now I need to choose locations for the 2 C's. How many ways are there to do that? Is it 7, choose 2? It's 4, choose 2, because I can't choose the 3 locations that I already have S's in them. And then double check, okay, it doesn't matter where I put the S's, so it doesn't matter what I did in the first choice. They're using 3 locations. There's exactly 4 left. There will be exactly 4 choose 2 ways to place my 2 C's in that thing. Okay. That's 4, choose 2. All right, so let's do that. I don't know, C and C. Choose the locations of the location of E. How many ways are there to place the E now? 2, which is 2, choose 1, where the 1 is because we only have 1 E. So that's 2, choose 1. Let's put the E there. And step 4, choose the locations of U. There's really no choice to make. There's only one option. And that's, we have one letter and basically one thing to choose and one thing to choose from, so it's 1, choose 1. Okay. So then the product rule says that the number of these words that I can make this way is 7, choose 3, times 4, choose 2, times 2, choose 1, times 1, choose 1. And that is equal to, I think it's 420, but I don't want to write the wrong thing down, 420. Okay. So is that clear how we got to that? All right. And so now let's see, for instance, why binomial identities are there's so many of them, and why double counting is such a powerful tool for proving these identities. Let's think about doing this a different way. First we'll place the U, then we'll place the 2 C's, and then we'll place the E, and then we'll place the 3 S's. So how many ways are there to place the u? 7, choose 1. How many ways now, after we've placed the u, are there to place the 2 c's? Okay, we've placed 3 letters. How many ways are there to place the e? 4, choose 1. Now we have 3 places left, and we have 3 letters to place. How many ways are there to place those? 3, choose 3, which happens to be 1. There's really no choice left. So that's by the product rule, the number of ways of doing this, of words that you can make like this is 7, choose 1 times 6, choose 2 times 4, choose 1 times 3, choose 3. Both of those things, this side and this side, both count the number of ways of strings that we can make. So, there's another identity for you. I mean, it's a boring one, of course, and it's one that's easy to verify when you, once you write this out longhand, you can just reorganize things and see that indeed these 2 things are equal. But it kind of illustrates, we basically use the same technique to count this thing 2 different ways. We just changed the order that we did things, and we got 2 expressions that, at least on the face of it, look quite different. But in any case, they're both equal to 420. Okay. So that's a sort of application of the product rule that's relevant for some of your assignment. Let's try another one. How many solutions does x1 plus x2 plus x3 equal to 11 have, where x1, x2, and x3 are all bigger than or equal to 0, and integer. So how many non-negative integer solutions does this equation have? Any guesses? So I'll tell you the answer. It's 13, choose 2. Any idea why? Yeah.
One of them could be 11 and the other 2 could be 0. So you could choose like where the 11 goes or something like that.
Kind of, yeah. And there's lots of ways you could attack this. You could say, let's try and use, for example, something like induction on the number of variables. In this case, you don't really need induction because things are finite, but you could say, let's try it where x1 is 11. Well, then there's only one solution. x2 and x3 are 0. But let's try with x1, 10. Then how many solutions do you have for x2 plus x3 equals 1, and so on. Grind your way through that and get the answer. And for some reason, it would turn out to be 13, choose 2. Or we can try and understand where this is coming from. So Any other things, examples that we know of where 13 choose 2 is the answer? And I don't specifically mean 13 and 2, where n choose k is the answer. So what kind of sets have size n choose k? Yeah. So so this is, I have a set of size 13, and I choose 2 of its elements. So let's draw a set of size 13. Make sure that I counted properly. Okay, so that's a set of size 13. And if I want a subset of 2 of those things, that means I pick 2 of them. So I don't know, maybe I'll pick this one and this one. Somehow from those 2 that I picked, do you see a solution to this equation up here? What's that? Yeah, so I can't take x1 equal to 5 and x2 equal to 10. You see another way to maybe interpret this as a solution? Yep. Yeah. So I filled in 2 of these 13 locations, and I have, that means that there's 11 that are not filled in. And these 2 that I filled in, they actually break this up into 3 intervals. And if I add up the lengths of these intervals, so this one is of length 4, this one is of length 4, and this one is of length 3. So I could imagine that that is a solution. I can interpret this as a solution. x1 equals 4, x2 equals 4, x3 equals 3. That's 8 plus 3 is indeed 11. Everything is bigger than or equal to 0, and it's integer, so that's one of the solutions that I want. Okay? So this looks like we're trying to relate the number of solutions here. So the set of solutions, we're trying to relate it to another set of things. And it's not a stretch to see that the other set of things that we're trying to relate it to are, for example, let's say, binary strings of length 13 that have exactly 2 1s in them. I think of this as a binary string where there's 2 1s in it and the rest is all zeros. Okay. So let's try and do that carefully and make sure that this is really what we want. So so this is a bijection proof. So A is the set of triples x1, x2, x3, such that x1 plus x2 plus x3 equals 11. X1, x2, and x3 are bigger than or equal to 0, and x1, x2, x3 are integers. So the size of A is what this question is asking about. Right? How many solutions does this equation have? B is equal to the set of 13-bit binary strings with exactly 2 ones, and therefore, so exactly 11 zeros. And I want to prove that the size of A is equal to the size of B, because the size of B, we can sort of get that directly now, because what's the size of B? It's just the number of ways of choosing from a set of 13 locations, 2 of them that are going to hold the ones. So the size of B we kind of get for free. It's just 13 choose 2. Now we just need to argue that A and B have the same size. And that means we need to give a function which will take something from A and map it onto something from B, and then show that that function is a bijection. Now you may have forgotten what bijection means, but we'll do that. So here's the function f from A onto B, from this set of solutions onto this set of binary strings. So if you give me a solution, x1, x2, x3, that will go to a binary string that starts with x1 zeros. Next is a 1. Next is x2 zeros. Next is a 1. And then next is x3 zeros. Okay? So if you give me, so for example, f of 2, 3, 6, starts with 2 zeros, then there's a 1, then there's 3 zeros, then there's a 1, then there's 6 zeros. Okay. So it's clear what this function does. You give it a solution to this equation, and it gives you a binary string. So now there's a few things we need to check. First thing we need to check is that this really is a function from A onto B. So what is B? B is the set of 13-bit binary strings that have exactly 2 ones. So we need to check that when we apply this function to a solution, we get a string of length 13. Well, what is the length of the string we get? The length of the string is x1 plus 1 plus x2 plus 1 plus x3, which, if we're coming from A, that means x1 plus x2 plus x3 equals 11. And that means this plus this plus this is 11, plus 2 is 13. So indeed, whenever you give me a valid input, one that comes from A, I'll produce you a string of length 13. That's one thing. The other thing that we need to check is that the number of ones is correct. So B is supposed to be binary strings of length 13 that have exactly 2 ones, but that's easy to check, right? We write zeros, then we write a 1, we write zeros, then we write the second one, and we write zeros. There's nowhere else that we put ones, and every time we do this, we write down exactly 2 ones. So indeed, this is a function from A onto B. But now we need to show that it's a bijection. Bijection means that it's onto. So remember, 1 to 1 means that I should never have this situation. I take an element from A and I apply F, and it goes to an element of B. And I take a different element from A and I apply F, and it goes to the same element of B. That should never happen. Okay? So and we're doing this slowly and carefully now, although I think already for most of you it seems obvious that there is a bijection between these two sets, but we need to just carefully check that indeed we satisfy all the rules. Okay, so if I give you, so that says, well, if I give you 2 different things from A, let's just make sure that those 2 different things go on to different elements of B. So I don't know, let's say one of the things in A is x1, x2, x3. And we have a different thing in A, we'll call it y1, y2, and y3. And what does it mean that these are different? It means that xi is not equal to yi for at least 1 I and 1, 2, 3. Okay. So they have to differ in one of the 3 coordinates at least. If they're the same in every coordinate, then they're the same triple of things. Okay, now we need to argue that, well, because they're different, then they'll map to different strings. So I don't know, we can do this slowly and painfully, looking at the cases. Well, what if x1 is not equal to y1? Then that means that f of x1, x2, x3 looks like this. And then continues. And f of y1, y2, y3 looks like this. And then continues. So it's pretty clear that this string and this string are not the same, because this string starts with x1 zeros, this string starts with y1 zeros, and x1 is not equal to y1. So those 2 are different. And if you want to, keep going, you can say, well, what if x1 is equal to y1? So case 2, x1 equals y1, but x2 is not equal to y2. Then if you draw the same picture again, you'll see that the x string looks like this, the y string looks like this. They're the same for a little while, but if these 2 are equal, x1 and y1 are equal, but x2 and y2 are not, that means that the location of the second one is different in them, right? Because this one is at location x1 plus x2 plus 2, and this one is at location y1 plus y2 plus 2, and those two things are different. So they differ in the second gap. And then there is no third case, because the third case would have to be x1 equals y1, x2 equals y2, but x3 is not equal to y3. Why is that not possible? Remember that this is supposed to be an element of A, which means that if I add up x1, x2, x3, I get 11. This is also supposed to be an element of A, so if I added up y1, y2, y3, I get 11. But if these two are equal, and these two are equal, and these two are not, then they both can't add up to 11, right? When you add up their first two things, you get the same thing, and then you add something different. One of them might add to 11, the other one not. Okay. All right. So that establishes that this thing is 1 to 1. To establish that it's onto, let's remember what that means. The onto picture was I look at A and I look at B, and I see things, all the elements of A, they go to something in B, but then you're left with a lonely element in B here that nobody in A wants to go to. So that's not allowed if this thing is onto. That's not supposed to happen. So what would that mean? What would that look like? Well, that's one of these elements of B are these binary strings of length 13 with exactly 2 ones. So that's 1, 2. So, just imagine there was such a lonely element in B, or rather take any element in B and now argue that there's some element in A that maps onto this thing. And it's easy to figure out what that is, right? You count the number of zeros before the first one. You get x, call that x1. Count the number of zeros between the first one and the second one, you call that x2, and count this, you call that x3. And now certainly f of x1, x2, x3 is this thing, and indeed we need to check that the x1, x2, and x3, that triple is in the set A, but that's easy to check. Its size adds up to 13 minus 2, which is 11, and there's no negative numbers, and they're all integers, so it's an element of A. So that is like a super slow, careful bijection proof that says that the set of solutions we're interested in has the same size as the set of 13-bit binary strings that have exactly 2 ones. Good? Now, I've been using numbers here, but actually, like the numbers 11, 2, which gives rise to the number 13, but there's nothing special about those numbers. Everything we just did, we can do for equations with more variables and equations that add up to any particular value. So just redoing exactly what we just did, the number of non-negative integer solutions to an equation like x1 plus x2 plus x3 plus xk is equal to n is n plus k minus 1, choose k minus 1. Okay. And that's just because the bit strings that I look at have room. They're a little bit longer than n. They have length n plus k minus 1, which leaves us place to put k minus 1 bits. And then we read off x1 as the number of zeros before the first 1 bit, x2 as the number of zeros between the first and second, x3, x4, and after the last 1 bit, we read xk. Yep.
Why is n plus k minus 1?
Because I'm going to drop k minus 1 ones into this string, which is going to break it up into k gaps between the ones. And so those k, I want the sum of those gaps to have length n. So they will have, they will have length n now because the whole thing has length n plus k minus 1. I've taken away k minus 1 places where I put the ones, so the amount of spaces that I haven't put stuff in is n. Okay. Clear? Good. Let's see how far we can push this. Good thing is I don't have to erase much. Let's say that I want to go further and say x1 plus x2 plus x3, it's not equal to 11, but anything less than or equal to 11. How would you do that? So is there a straightforward way we could just grind it out? Yeah.
You could solve the same problem, but use 10 instead of 11, and then solve that, and then solve every number before that.
Yeah. So we could actually read it off, right? So I know from this lets me use any n and any k. I don't need any k. I still only want 3 of them. But from this, I can say, well, the number of solutions is where x1 plus x2 plus x3 are less than or equal to 11 is the number where they add up to 11 plus the number where they add up to 10 plus the number where they add up to 9 plus the number where they add up to 8 and the number where they add up down all the way down to 0. That's good. We'll have to be a little bit careful at the beginning of that because we'll be asking for things like, if we try and exactly do this, we'll run into an issue where we're trying to get x1 plus x2 plus x3 to add up to 0. No, that's okay. Even that's okay. So, so here's the sort of boring answer. You just sum up k equals 0 to 11 as nice as I would like, but it is an answer. I'll tell you what the truth is, and then maybe you can give me a proof. Although, again, we're about to, just by doing this, by giving this ugly answer and a clean answer, we'll have proven another binomial identity, just by accident, basically. So I claim that the answer is 14, choose 3. Yep.
Sorry, can you explain why it's k plus 2, choose 2?
Why it's k plus 2, choose 2? Because we're going to look at all of the, so if we look at the theorem over there, in fact, maybe I should have changed variables and said, I'll take n running from 0 to 11 of n plus 2, choose 2. That doesn't change anything significantly, but it makes it look more like the thing on the right. So what we said is if you have k equals 3 variables, then the number of solutions is n plus k minus 1, choose k minus 1. That's for the solutions that add up to n, and we're interested in all the n's from 0 through 11. Okay. But I'm telling you that the answer is 14, choose 3. Now that you know the answer, can you think of a bijective proof? Any suggestions? Yep. I'm just telling you that's the answer to this question. So I'm giving you a hint. The hint is here's the answer. Now you just prove that it's the answer. And you can take out your notebook and simplify the sum, maybe use some of the identities we know and show that those two things are equal. But there's an easier way to see it. Yeah?
So you just do those and dump the
Yeah. So take, we'll use, let's say, a bit string of length 14 that has exactly 3 ones in it. Like here, here, and here. We'll call this x1. In this example, it's equal to 3. Call this x2. In this example, it's equal to 2. And we'll call this x3. In this example, it's also equal to 2. And we have no name for this. Now, is that a solution? x1, x2, x3, they're all integers. x1, x2, x3, they're all bigger than or equal to 0. And if I add them up, they don't add up to more than the number of blank spaces here. Well, the total number of spaces is 14. 3 of them were filled with 1s. So the number of blank ones is only 11. And these 3 things then, they can't add up to more than 11. So indeed, that's how I get an answer. And now, if you're a masochist, you have to then say, okay, let's carefully check that indeed there is a function between these bit strings of length 14 that have 3 1 bits, exactly 3 1 bits, and solutions to these things that where x1 plus x2 plus x3 is less than or equal to 11, an integer, and so on. And that means you need to check that define f. We can sort of see how we define f, right? The string that we write has x1 zeros, then a 1, x2 zeros, then a 1, x3 zeros, then a 1, then it'll be 11 minus x1 minus x2 minus x3 zeros. So that's what the function will look like. Carefully check that indeed that gives you what you want, and check that it's 1 to 1, that you don't have 2 different triples, x1, x2, x3, and y1, y2, y3. They give you the same string. Again, there's nothing new there. And check that it's onto, that there's not some string that I can write here that doesn't have a corresponding solution. But the corresponding solution is easy to read from the string, right? You just count number of zeros before the first one, number of zeros between the first and second, number of zeros between the second and third. That's a solution. Okay. Yep.
So from the question they say is it has to be less than or equals to 11. So how would you get 11 from your solution?
As long as I place the final one over here, I will get a solution that adds up to 11. So all the solutions that add up to 11, they're the ones where the final one is over here at position 14. Because then that leaves 13 other slots. 2 of them are occupied by 1s, so that leaves 11 blank slots that get counted. So moving the 1 over here increases x3 to 1, 2, 3, 4, 5, 6. And hopefully 6 plus 2 plus 3 is indeed 11. Right, so, and actually you can kind of see what's happening, right? What is this formula here? The way to interpret it is, well, I can place that third one over here at position 14 and then look at the ways of doing the other 2. That gives me the 13 choose 2 term. Or I can put it, the last one at position 13, and then I'll get a 12 choose 2. Or I can put it at position 12, and then I get 11 choose 2, and so on. All the way down to that third one can't go sooner than position 3, because you have to leave room for the other 2 ones, which gives you exactly that formula there. But, I mean, that also gives you this identity here, which yeah, I don't think any of the ones we've done give you that immediately. Okay, and of course that generalizes. Nothing special about only 3 variables, and there's nothing special about the value 11. Yep.
How would you place it so that you have x1 plus x2 plus x3 to equal 0?
x1 plus x2 plus x3 equals 0. Does anybody want to tell me the answer? Yep. Yep. 1, 1, 1. How many zeros before the first one? 0. How many zeros between the first and second one? 0. How many zeros between the second and third one? 0. So that's x1 equals 0, x2 equals 0, x3 equals 0. But that's a good question, because never in any of my examples did I put 2 1s side by side. What happens when you put 2 1s side by side is you interpret that as meaning there are no zeros between those 2 1s, which is perfectly valid. Okay. So, second theorem. Eleven plus 3, choose 3, or in general, n plus k, choose k, not equals n, less than or equal to n. And as a bonus, you get this identity, which is the sum k equals 0 up to n. No, n. I don't know. Let's say x up to n of this guy. This is n plus k minus 1. Choose k plus x minus 1. Choose x minus 1. That these two things are equal. Okay. Okay. So any questions? Yeah.
What would you do if this was a restriction on the size of x1, x2, and x3? Has to be greater than 2.
Then it gets harder. And you are probably, maybe if it's a uniform restriction, there's a clean formula for it. But if it's a, yeah, even then it's not immediately obvious. Yeah, then there's, I think you'll end up having to do some case analysis, because if you try and use something like the product rule and say, you end up having to look at how many bit strings there are where the distance between, that have, let's say, 3 ones, and the distance between 2 consecutive ones is at least 2. Work through that. It's not immediately obvious to me how you attack it. Yeah?
The same theorem applies if you have all the x's as negatives.
If they're allowed to be negative, well, then you can have infinitely many solutions, because you can always have you can have 11 plus k minus k for any integer k, right? So then counting the solutions doesn't make sense, or if you count them, you just say there's infinitely many solutions, because you take x1 equals 11.
Negative. So and the solution has to be negative. Does the same theorem apply?
Sure, if everything is negated, then yeah, you can just multiply both sides of the equation by -1. If it's an equality, that's no problem at all. If it's an inequality, when you multiply by -1, you have to invert the inequality. So it will apply to things like minus x1, minus x2, minus x3 is bigger than or equal to minus 11. But it's just another way of writing exactly the same thing. Because of course you can't use this to count things like x1 plus x2 plus x3 is bigger than or equal to 11, because there's infinitely many solutions to that, obviously. All right, so let's just think about why this is sort of relevant for you guys. So what kind of situation is this modeling? Well, I mean, this is basically just saying I have a bunch of work to do, n units of work to do, and I have k people or k processors or k whatever, let's say processors available to do that work. And so how many different ways are there for me to distribute, how much work goes to processor 1, how much work goes to processor 2, processor 3, and so on. And there may be sort of other things interacting with this. And so you can think of many sort of solution spaces for assignment problems look like this. And when I say assignment problems, I mean problems of assigning work to processors or work to various things. And now you can ask, well, there's lots of ways to do this. Which way is the best? And one option is to try all the ways, all the different possible, how much work should x1 get, how much work should x2 get, how much work should x3 get, as long as all the work gets done in the end. Think about trying all the different possible ways. That's a potential algorithm for figuring out what the best one is. But if that's your algorithm, is to try all possibilities, then you'd better be sure that the number of possibilities is not outrageous. So here, it's not in terms of what computers can do. 13 choose 2 is not outrageous, and neither is 14 choose 3. But when faced with a general thing, it's nice to have a formula to say, okay, it's reasonable for me to try some rough solution that it tries every possible combination, or to say that's unreasonable, I need to come up with something better. So ultimately, this is really why combinatorics is so important to computer science, is the sets that we're often counting are the number of things that a computer has to try before finding the best one. And so ultimately, we usually want to know the sizes of those sets because we want to know how long it's going to take for the computer to try them on. Okay. So we'll leave it there for today.